Good afternoon, everyone. My name is Hao Zhuang from Dhaka University. I think this time we need to introduction our jury. So let's welcome our jury. Please go ahead to introduction yourself.
I'm Lin Daoxin from Donghai University.
来自中区外校。
我比中正大学物理系。
And before we start our presentation, so everyone have to take off your mask when going to speak, okay? Because the sounds we have want to listen very clearly. And I think every group has to introduction yourself, the chaplain or the reporter. Please introduction yourself and your team member.
Hello everyone, we're team from Qingxin Academy. I'm the captain Qiang. This is Yang Xiangru, Wu Zhenyan, Yu Hong, Zhang Youzhang.
Of the review.
Hello everyone, we are team 1. We are team B1, and I'm Zhang Yixi, Lai Xingyu, Luo Henli, Zhang Yiti, and Xu Shaohen. Thank you.
Hello, we're Ayuan A1T3 from Wuling High School. I'm Yu Xiuxian. This is Qiu Guowei, Wang Bohao, Wu Jiaha, Chen Yingshi.
Okay, thank you very much. Because we are very special, we already have the problem, right? Problem number 10. So, sorry, I didn't forget. Okay, please touch yourself. Sorry.
I'm sorry. My name is Andrew Lee. I'm the leader of the Dhaka University. This is Bernie. This is Hans. This is Howard, and this is Dan. Thank you.
Okay. The attention of every group, please write down your names on the board, okay? So now we have 5 minutes for prepare, okay? We already start the 5 minutes, okay? Okay. 这个 P 的人，他现在是这一组弄出来，他就有限制嘛。这些都删掉，他们就先删掉，只有这一个乱。
我通常只是直接分享。
我
4 goals, and I'll be talking about the problem magnetic field. So first, I'll be talking about the problem statement. Take several identical fidget spinners and attack neodymium magnets to their ends. If you place them side by side on a plane and rotate one of them, the remaining one starts to rotate only due to magnetic field. And investigate and explain the phenomenon. So our main focus will be investigating the reasoning for the spinning of the fidget spinner and what parameters may affect the spinning. And this is our outline. So first we have the observation. So we can see that when we spin one of the magnetic plates, we can see if we place magnetic nuts in the middle, the other plate will start spinning, which I think this may be caused by the magnetics repelling and attracting each other to create the torque of the spin, which I will further explain in my theory. So this is the graph I draw myself. And from this we can see that if we think the red circle or the oval are the end pole and the blue is the S pole, we can see that once we rotate this plate over by for example 30 degrees, etc., then this red end plate and this red north pole will repel each other, and so does the other four. And after all the repelling force, we can see that the torque will make this to spin in the opposite direction, which means that if we turn this by 30 degrees clockwise, this one will turn 30 degrees counterclockwise. So our theory is temporary magnets, which when a block of metal is featured with a permanent magnetic field, the block of metal will be magnetized to reveal a certain pole. And then the magnet and the metal will be temporarily magnetized and will become a temporary magnet, and the magnetic field will disappear when the environmental magnetic field is removed from the system. So for example, we take this as an example. So if we have the N pole and the south pole on this side, we will see that due to the influence, this metal, which originally doesn't have magnetic field, will be influenced and have an S pole on this side and the north pole on the other side. And the fourth analysis is I want to talk about how I want to understand the force. It's like what parameters will affect the force. Which if we take two permanent magnets and it will create a force that is like this equation on the bottom, where Q is the magnetic charge of the magnets and R is the distance between the magnets. And the result, if we use the same magnets, they will have the same magnetic charge and the coefficient. So and plus 4 pi is already a constant. So we can see that F is inversely proportional to R squared, which is like gravitational force or electrical force. And combining those two theories together, we can see that the middle metal pieces we assume is the middle plate, which will be the metal nuts or nuts and bolts. And both sides, this is the first plate and this is the second plate, as I shown down here. So when the first plate has the north pole right here, it will influence the middle nut, the nuts and bolts. And so this side will have the south pole and the other side will have the north pole. And because this side, originally when we set up, this is north pole towards this side as well. So the north pole and this north pole will repel each other. So when we spin, the repelling force will cause will create a torque for the whole plate to spin. And for the experimental setup, we use 2 plates of wood and cut holes to fit different amounts of magnets into the wooden plates. And the magnets we use are the same neodymium magnets as the problem statement stated. And we use 12 metal nuts in the middle to transfer the magnetic force. And for the variables, we control the magnets that we use and the wooden plates that we use to place the neodymium magnets on. And the independent variables is the number of magnets in the plate, which I'll explain later. And the dependent variable, we will see that if we rotate one of the wooden plates for one whole revolution, how many revolutions will the other wooden plate experience? So this is our data analysis, which we can see that this ratio is the number of magnets on the first plate, which is the plate that we will spin one whole revolution, and the second plate, which is the one that will be affected by the repelling force and spin correspondingly. So for example, this is 12 to 2. We can see that the revolution, if we turn this 12 magnet plate once, we can see that the other two magnet will, the two magnet plate will rotate 6 times. And for the others, it shows like this graph, which we can lead to the conclusion is that the number of revolutions is inversely proportional to the number of magnets we have on that side. And we can think of it as like a normal gear, because like each gear has its point, and each point will be stuck together one by one. So we can think that, for example, the 12 magnet, it will have like we can think of it as a 12 gear, normal gear, and the other is a 2 gear or 4 gear as example. So we found out that it works very similar to just a normal gear without magnet, just using only contact force. But side by side also has another meaning, which is when one of stator spinners starts to we place 2 stator spinners side by side, which means it's not parallel to each other, which they're all on the same plane. So for this experiment, we can observe when one of the stator spinners starts to spin, the other spinner will start from a static, which means it won't have an initial velocity, and then it will slowly start to spin and decrease, and it will slowly start to spin and increase in angular velocity, and the other one will slow down, and due to the magnetic forces. So we can explain by not only because of the magnets repelling and attracting force to create a torque, that there are not only do we consider that, we can also consider that because if there is other resisting forces that will explain further, so that it will actually cause the loss of energy, which I will explain where the cost. How do I define the loss of energy? So this is the observation, which is these are 2 fidget spinners. So when I set this one to a rotation with a certain amount of angular velocity, so these magnets will have magnetic force, which will be repelled and attract at the same time, which I will explain in my next slide. And due to the magnetic force between these magnets, if this spins this way, then in the end we can see that once this reaches maximum angular velocity, this will become stationary, and this will spin in the opposite direction, which also I will explain in why it will spin on the opposite direction in my next slide. Yes, so on this slide I will talk about the force that is mentioned, which is mainly just magnetic force. So for example, we take 2 fidget spinners as an example. The magnets placed in the opposite poles will generate torque from magnetic forces. And the distance from the middle, so we count the force arm from the middle of the magnet, from the fidget spinner, which is here, to the center of the neodyluvian magnet, which is here. So we think that this part is the force arm, and we can see there's a force arm here as well. And because we place them interchangeably, which means that if this is N, then this will be S. But because this only has 3, so this is completely and this can be random. So and this is like this. So when the magnets are aligned in this specific way, we can see that the north pole and this south pole will have an attracting force, and this north pole and this north pole will have a repelling force. So when this is stationary and this is spinning, this will cause this will generate a torque that will turn this counterclockwise, and this will generate a torque that will also be counterclockwise. So we can say that when this is spinning clockwise this way, then this will generate a torque this way, which is counterclockwise. So they are in opposite sides. They will spin in opposite directions. And the magnetic force is the same as before. And the energy loss, and for the energy loss, we use a special equation called the Stanley's equation, which if this is the situation, which is one of the magnets starts to spin, the other will be pushed due to magnetic field. And if this is a scenario, the relationship between the energy loss and the frequency will be an exponential relation according to this equation. So I will be explaining this equation here, where the PC is the loss of energy in rotational energy. And Ka is the anomalous eddy current loss coefficient, which will be a constant. And F is the frequency of the spinning, so of the spinning magnetic, spinning fidget spinner. And the B is the magnetic flux density. So to explain the energy loss, I use the I use the spinning kinetic energy. So which will be this like this. And so the loss of energy will be which will equal to this equation according to the equation. So the I is the moment of inertia, and the omega I is the angular velocity of the first fidget spinner, and the omega F is the angular velocity, is the maximum angular velocity when the first fidget spinner stops spinning. So the methodology is we will use a motor to spin in a constant velocity. So the fidget spinner will have an angular velocity, and we will do the relationship of the RPM of the motor and the fidget spinner on our next experiment. So this is our variables, which is the independent variable is the revolution per second of the fidget spinner. So from this we can see that for every 2 revolutions, we can see there's around 1 revolution, and we can see the same relationship between the motor and the fidget spinner, which we can see from this graph, which is almost 2 to 1. So we can conclude that if we want the fidget spinner to turn 2 times, if we want the fidget spinner to turn 1 time, the motor will have to turn 2 times. So the RPS of the motor is 2 times the RPS of our fidget spinner. And this is the data analysis of our initial RPS of the fidget spinner to the loss of rotational energy. Which, if we place this onto a graph, we can see that the fitting graph, the y, which is the loss of energy, is proportional to 3/2 to the power, which will fit our theory. So the conclusion, we can confirm our theoretical model through the graph we fitted, and the correlation of the 2 spinning magnetic fields is an exponential relationship with the power of 3/2. And I think that is the end of my presentation. Thank you.
Thanks. So now we move on to the question from our opponent.
Okay. First, I want to ask you, done 2 kinds of experiments, right?
Yes.
But the normal only acts based on the same plan.
Because we did it 2 times, because they said if you place them side by side, but they didn't say like what you said, like on the same plane.
Okay.
So I don't know which one. Yes.
Okay, and I want to see the middle part of this experiment. Middle part matter.
Oh, you mean the middle part? This one. Okay.
Just think the middle, the number. Okay, it's a middle part, and this is iron. Is that iron?
Yes, that's iron. Or you can say steel. Yes.
Okay, then I'll take a look at your energy loss.
Energy loss.
Yeah,
This one?
yes. Right. And you consider your only energy loss is caused by the electron.
What? By
You
what?
consider your energy loss only because of the electron.
I didn't. No, I said the energy loss is a combination of, for example, air resistance, non-ideal environment, and friction that will also all contribute to the energy loss.
But okay. Then, right, that's all. Thanks.
Okay. So now it's time for
do the summary first. And then here, take several identical things in it, and place them side by side on the set. And rotate one of them, the remaining one starts relating. And okay, these are something I think they should do when during this question. Set up according to the proper definition and accurate and reliable device for complete explanation of the phenomenon and the simulation for possible motion is battery. Right, and this is the summary of the reporter. He used a theory to describe the magnetic force and set up different relation ratios for the first device and the second device and discuss the energy loss. Right, these are some pros and cons. Clear definition and focus on the problem. And relation ratio listed in the chart and the two variations of them here to discuss. Variable or short curve. And the cons are the first device did not match the problem's requirement and they didn't use the magnetic charge they used. Okay, can we go into the discussion?
Yeah, sure.
Okay, then the first question about your algorithm, our technique. Right, and how do you think the metal part will influence the spinning?
Right. We think that because this is like a middleman for the whole magnetic pole. So if this it has like the number has to match in order for the whole thing to work.
If the downward part is 12 and upward part is 6, how many metals should you replace?
You mean the middle?
Right.
Because it is 12, so I think 12 will be a good number because it has to like one by one match the top 6 for the metal bolts.
Okay.
I need to draw.
Okay.
Clear
Okay.
for you?
Okay. For clarity.
So I think for example the bottom plate is 12. So that means that I don't think first.
Right.
So in order for this is the layer 1. And if this this is the conveyor. And then so in order for this to work is that for example for this they have to be different. For example if I use 12 manifolds like this.
Yeah, all attached and
Yes, and then
check.
so these two due to influence on the third layer. So for example, if this is n and this n and this n, then this on the top will be n. Like this. And this will be corresponding to this. So this will affect this whole magnitude.
And for 12 and 8.
They will need you will need to do drawing you will need to draw out the layers and look at how to correspond each of them. But usually maybe multiple on the top one.
Okay, they will spin at the same direction or
I think it will be opposite direction.
in 12 and 12, 8
Yes.
and 5.
And what because I think from this you can see that when you rotate one, the other one will have the repel force to the other side. And maybe it's not clear enough here, but I draw and maybe so this is the bottom. So I think I call the bottom maybe the lower layer.
Right.
And the yellow one is the top.
Okay.
And for example, you said I take four magnets here. And the one magnet are below, so they might be like this. So after I turn the top layer, maybe like this, So it would look like the top layer would be like this. And white will be original, and where is original?
Okay, so if the speed is too fast, is it possible for the gear overload? That if the speed is
Oh yes, of course. It's like I said, it's like normal here. If it is too fast, for the transfer will not be.
Did you consider push adjacent the angular velocity is too fast for the gear to work?
I think the parameter I did is different. Like you see the revolution between how revolution affect magnet amount affect the revolution. So I turn the top layer very slowly to prevent this from happening.
Okay. Now move to your torque. Right.
Do you want to? You mean the second fidget spinner?
Right.
Okay. Oh yeah.
How will you define the force arm?
Force arm. I think like for that example, like a fidget spinner. Like this is the middle, right? And this is the 3 magnets that I use. Then I think that, for example, because from the observation we can see that fidget spinners only spin on the outer side, right? Like the middle here doesn't move. So I set this here to be the tip point where it doesn't move. So the force is from like this magnet to this magnet, and then it will be like this is the center of the circle. And because because like 2 forces, there are force and counteractive force. They will be on the line. They will be on the line of this line of the 2 circles. Yes. So I use the center of the circle and see the force will be this way and this way. So I use the torque here.
But if you consider the magnetic charge, you consider that, and I think in this part the force is bigger and the upper part will be smaller. So I think if you need to calculate the force on, you shouldn't set your tip point at the central or accurately.
Yes, I guess like there's many different the charges are different, but I think that for example, if we have like a metal ball with a positive charge, like we don't always know like there are not evenly dense, but we can sometimes see it as like a point charge. So in this experiment I simplify it to like a point charge of magnetic.
Okay, simplify the
Yeah.
visualization. And next, we want to move to the eddy current part. Energy loss.
Energy loss.
Okay. The loss of energy. You only consider the eddy current part, right?
I didn't talk about eddy current in my.
And
Yes, I didn't include it.
and plus this
Do you want to actually the reason?
reason why you can
What is P? I think PC is the energy loss. Yes.
it's the eddy current.
Oh, you said this eddy current. Oh,
Okay.
this is like this is a coefficient like for because normally there is the eddy current.
Wait.
Like on the magnet because like the magnet also like metal.
Does there a true current on the magnet happen?
True current. I didn't test with setup, but because I use this formula, so I think that I only talk about because this is the same value, so I just want to fit the PT to the frequency.
Okay, so you consider your B valve changing by time, like this, for a single magnet, like this, right?
Yes.
Or complex situation.
Yes, I think it is like a sine wave or cosine wave. Right?
And how to define the frequency?
The frequency is like just like a normal wave, like this part.
And is this very simple?
Is it because for if we only look at one, if we don't
One magnet, right?
yeah, if we look at only like one magnet, then this gives out magnetic field, right? And it gives different magnetic field on different points. Like for example, if it's here, at different places, the magnetic field is different. Yes, right? So once it's been one whole round back to this place, so it will start like another thing, right? Like if I turn this one whole time back to this point, this will be the same as one revolution ago, right?
Right.
So yeah, so I calculate this frequency that way.
But if it is not a very simple sine or cosine function, if it is like this, it's probably.
Yes, but okay, we continue.
Okay, then next I want to take a look at the energy results to consider. All right, how would you define this? This is two magnets. Is this the rotational energy of two spinners or one single spinner?
You said what? You said energy loss?
Right. For one.
I use like because from the observation we see that after one fiddle spinner finishes spinning,
Right.
the other will start to spin. So I think like energy will be transferred from this to the other spinner. So I calculate the difference. Like for example, maybe this is 2, and then it transfer over to 1. Then I subtract these 2.
They only spin for one round.
No, it's been multiple rounds, but it slowly gets slower and slower every round. And at one moment it will become stationary, which means it won't move. Like
Okay, so I consider the energy to like for the first spinner it will be like to 0 and here to here.
Yeah.
Like this.
I think
Other should be here.
yes, but I think this one should be higher than this one because every transfer there should be
Alright. So you consider transfer. The energy decrease this way.
Yeah, it's there.
And the result is proportional to the
To the frequency, angular frequency.
And did you consider that the combination of the air resistance and the air resistance can be proportional to the omega squared or omega.
Can you explain more like what do you mean by like the air resistance?
Our opinion is.
Or do you want to write the formula out for me?
Okay. The air resistance can be proportional to the V squared. So for this spinner, it can be omega squared, right?
Yes.
Or omega. Because of some
So I don't think
things.
it's omega, but yes, omega
Right.
square I understand.
Right. These are some.
Oh, you said possibility?
Right. And the friction can be proportional to the friction could be a constant.
Yes, I agree.
Right, so these can combine your data not only because the is accuracy, right? Accuracy.
You mean
Right. So your conclusion is only the accuracy will influence the energy.
I think because maybe there are like more like maybe I use the
Sorry,
wrong.
hands up. Okay, move to the next stage. Can you summary?
Okay. Then for the maximum speed that can make the gear work well, they didn't do the experiment. And for the eddy current, they think their conclusion is the eddy current is the main of their energy loss, and not considering other possible factors. Okay, these are my summaries.
Okay. Okay, so we move on. The next one for the mirror.
So I would like to ask for opponents and reporter about because you previously mentioned that you always control the rotation of the fiddle spinner. But what do you think when the fiddle spinner is spinning too fast? What will happen?
If like I tried like at the start for our demonstration, like for our observation, I spin it very fast. But then in the start, the energy transfer wasn't very successful. But as it gets slower, the energy transfer starts to go to the other fidget
So
spinner.
what did you observe?
I observed that at a certain point, like it will the energy, but if one goes to stationary, the other will start.
What about you?
I think if the angular velocity is very fast, it's not possible for the gears to work well, and I don't think if the motor can stand it, so we push.
So our observations when like angular velocity is too high, we observe it will actually oscillate. So it might be different from your opinion. But the next question will be about like what do you think to the reporter, what do you think about how much influence the air resistance and kinetic friction will give the spinner? Because you also mentioned the energy loss and also points out the eddy current and also air resistance.
To conclude is that the K I used, maybe I put the wrong tag because I thought I was calculating that, but in the end, what I got from my experiment should be like a combination of all of the energy loss. Yeah.
Thank you. So to both reporter and opponent, I would like to ask you guys, what about how the changing of angular velocity of the first spinner would affect this phenomenon?
You said
For the angular velocity of the first spinner.
effect, how it affect the second.
Yes.
We think that if it is too fast, it will not have a successful transfer.
So it won't rotate, right?
Even like if it's always that speed.
I mean, like the first spinner will not affect the second spinner just like two rotates.
Yes, if it is always so fast.
It's just the same that like the gears overloaded, and also energy loss we consider at the same when these two spin are the same direction and the magnetic energy are the same.
Okay, so do you think that the angular velocity of the spinning will give you a magnetic or a different result?
We think that like if you spin it very fast, the second spinner, although
Okay, I think you're always answering the same thing. So what do you think that the spin, how do you know the spinner won't spin the other way due to the torque?
because from
Sorry, time's up. You have 2 minutes. Okay. You take the floor.
Honorable judges and fellow debaters, this is Team B1 reviewing problem 10 magnetic theory. So this is a problem statement and the reporter are focusing on the reasoning behind the spinning and also explaining to summarize the report, they explain the phenomena as one spinner, if they spin one as a magnetic plate, another one will also start to spin. So they consider it as a temporary magnet, and also they do the magnetic force transfer from one plate to the other, and it is also because of the repelling force and other resisting force acting on it. And they conduct two kinds of experiment with a vertical setup and a horizontal setup, which with the vertical setup they do the experiment regarding the number of magnets in the plate, and for the horizontal one they varies the revolution per second. So regarding the reporter's presentation, we think that they did a really good job on detailing explaining the observation and theory variables, and also they had a really great demonstration on experiment setup. However, since their last experiment proving their theory, I think they should have more improvement on it, and also they have lack of consideration about the magnetic force of the static fidget spinner. And also, it should have more explanation on the rotational inertia as they mentioned it. And regarding the opponent, we consider that they have a really, they do consider the relationship between a magnet and metal part between it. And also, it's good for them to mention the air resistance as a part of energy loss that the reporter missed. And however, they have lack of consideration about the influence of angular velocity during the distortion. So they first discussed about the structure of the device, which the opponents question about the magnets in the middle part. And reporting think that 12 magnets will be a pretty suitable number for it, and the 3 layers of the vertical device will actually correspond with each other. And the rotation is because of opposite direction of rotation is because of the pole force. And we have to be sure that the setup of the middle plate will actually really correlate with it. And so the second thing is tells about whereas the plate spins too fast, there will be no gear, which should be a boundary condition. And the reporter said that they control the device to rotate slowly to prevent the condition. And we believe that this should be a boundary condition that should be included. So next they started to define the force on rotating and where's the center regarding the graph the reporter drew and slides. And we believe that if this simplification should be explained more detailed for confusion. And next on they point out the energy loss parameters, including eddy currents, air resistance, and opponents think that they shouldn't be simplified to just the geometry questions. So the reporter answered it with the fit of the energy loss frequency, and they only view it in the magnetic term. So we believe that the frequency would change along with the loss of energy. And at last is a function about air resistance, which the reporters think should be added to the equations, and we also believe that it should be added. So that's regarding the missing points. We think that the reporter and opponent should add more on the boundary condition of velocity, and also they might do more experiment on the direction of magnetic force. Thank you.
Okay. So the report to complete the conclusion.
I will make my conclusion. First remark is the fidget spinner rotates because of the core gear created by the magnet repelling and attracting force, which is mainly derived from the magnetic force between the aluminum magnets. And the second is the number of revolutions is inversely proportional to the number of magnets on that side. If we're looking at parallel wooden plates. And the correlation of the two spinning magnetic gears is a special relation with the power of 3/2, which is the result we got if we place the two fidget spinners side by side on the same horizontal plane. And we think that the 12 magnets will be a good middle layer, whilst with the 6 and 12 on the top and bottom. And the opponent pointed out that the Ka is the anomaly eddy current, which we then after discussion we found out that the constant that we got is not the constant that I wrote. It should be the combination of air resistance and friction. And we didn't conclude the main factor will be the anomaly edit coverage. I think we will be correcting that data in the future. And if we think that the area velocity is too fast, the other one will oscillate. It will look that it's not moving, but it should be slightly oscillating or vibrating. So that concludes my remarks.
Thank you. Okay, so now time is for our jury. Any questions for our jury? Yes. Question for you three. So you have a equation for the force or magnetic force, and for magnetic charge. No? So you can change to that one. Look like this one. So is this equation right? So how to define the magnetic charge?
Magnetic charge is the charge that is regularly used in the Maxwell equation, and of course it's an assumption that there are magnetic monopoles.
But that assumption is not right.
Yes.
As a single magnetic dipole, they can consider there is a very small distance of positive magnetic charge and negative magnetic charge, which create a magnetic field like electrical dipole.
Yeah.
Yeah. So the B field of the magnetic charge create is like the E field, the real charge create.
So okay, and the review. Hello.
Oh, sorry. So I agree with the opponent and think that it should be more like related to the magnetic dipole moment, which somehow is related to this equation but not perfectly correct.
Okay.
Do you think this formulation in your model is really correct? Because in my opinion, this formulation is only for static magnetic charge or fixed confine the magnetic charge. So you can define the distance between the magnetic charge. But in your system, when the spin starting rotate, the magnitude and the direction between the two magnetic magnet or magnetic charge is changed. So your force is time dependent. You see? Yeah, so in my opinion, this formula is only for static charge or fixed charge. Only for one moment, only for a single moment. Do you think?
Yes, I think I made an assumption that this can be a little like this can kind of fit this situation, but yes, in reality it is changing.
Yeah, if your charge is moved, this formulation is not work. You need to add in some time dependence.
Yes, variables.
My opinion is for the point magnetic dipole, but the magnet have the significant size.
Yeah,
not just a
but
point.
you shouldn't consider the time dependence here. This is for static charge. The charge cannot move. And the force is we can write down this.
So if
when
they are
charge is
moving,
moving,
the V field is changing, and in the space there will be some electromagnetic wave.
Yeah, and the charge is yes, sir. And the charge is moving. The field propagate here need to time retarded time, not instance. You know that when the charge is moving to here, the field propagate here needs some.
Is a form of
So this formula is charge to charge, point to point. But I think the moving dynamic system should be using some field concept in here, maybe. It's good.
Yeah, I agree. I think this formula should be used in a static, not in a more like moving state.
Okay. Any follow-up question from jury? No? Yes. So all you mentioned the eddy current. So do you think that the frequency of the rotation is large enough to create a significant eddy current? Do you think the frequency is large enough?
My opinion is we don't know the coefficient or somehow the resistance of the magnet, because the reverse state, the eddy current loss is caused by the eddy current inside the magnet or hot. We don't know some coefficient, so we can't do some prediction that if the eddy current energy loss is quite significant or not. So the final energy loss.
Time up. So if you want to answer, reporter of the reviewer.
I want to extend more, explain more is that originally that shouldn't be eddy current, but if you were to consider like eddy current, I think the change of the magnetic field should be large enough. So I think we need more research on like what if this magnet will be affected by that. Yes.
Okay.
So we don't actually think eddy current is that significant, but the energy loss will be, but it's not the main factor for the energy loss.
Okay. Okay. So now we need to write it slow. Okay, so eddy current show the Euler plot for the okay, 6, 6, 7, 7, 7. Okay, the next one is for the opponent. Okay, 6, 5, 6, 6, 7. Okay, the next one is for the rebuilder. 7, 7, 7, 6, 7. Okay. Any questions? No. Next we have the